So, in the last class we have been talking about the shifting of weights from one side of the vessel to another by a small shift. If there is a small shift of w d0 of a small mass, what will be the distance through which the center of gravity of the whole ship will shift. Now, we come to a new type of effect that we call as the free surface effect. Now, this in your course of study here, you will see free surface effect used to denote two things, means two different things which are both are called by free surface effect. That is, one is free surface effect as you see it in hydrostatics here that we are going to do. Then you will see another free surface effect that will come in your marine hydrodynamics, which Professor Sen will be teaching you. He will be teaching you, and Professor Sahu, they will be teaching you about waves and all that. There another free surface effect comes. I will tell you what the two things are. First of all, let me tell about what they are talking about. Free surface effect means the effect of the air sea interface. Means we have talked about a water line. So when you have a ship, we talked about a water line. So in general, this has a movement of its own. This is the water line. This is the surface of water that has a movement of its own. For example, when a wave passes through it. So when a wave passes, okay, the free surface will become like this. This will become like this. It's not a straight line. Now, when we are studying the effect of this, means what is the speed with which the wave is moving, what is the displacement of this free surface from the mean position, like that, that study is called as free surface effect in their terminology. So that is their free surface, that comes actually in waves and hydrodynamics, marine hydrodynamics. So now what we are doing is a free surface effect that we talk about in hydrostatics, which is different from that, but not very different. That is, the meaning here is, when you are studying the free surface effect, what you are doing here is, suppose you have a tank in a ship, means, okay, let me draw a ship like this. Now suppose that there is a tank in the ship, means this much is a tank. Okay. Now in that tank, let us suppose there is some liquid. For example, you can have oil tankers which carry oil. They will have huge tanks. In fact, they have only tanks, mostly only tanks, and they carry oil in it. Or ordinary ships itself will have in it huge tanks which will carry ballast water. I have already told you what is ballast water, taking in and leaving out of water for going up and down. So that is also having a tank of its own. So these things, you will have something, that is, you will have a tank which is not fully filled with water. So that means you will have a free surface of liquid. That situation where you have a free surface of liquid in a tank inside a ship is known as a free surface effect in hydrostatics. So it is actually a free liquid surface or liquid surface in a tank inside the ship. You have to note that if the tank is completely filled with the fluid, what is the difference? The difference is that you won't have this movement of free surface. It will be fixed. So it will be just like a solid. It doesn't make any difference. That liquid becomes just like a solid and it moves with the ship only. There is no separate motion of its own. But if it is not filled, this free surface will move like this, and it has a effect of its own on the ship's stability. So that is what we are going to look at next. That is what we are meaning by free surface effect. Okay. Now let us see what that is. So let us look at a cross section of the ship. This is a cross section. And let us suppose that in this ship, there is a tank like this. It does not matter where it is, but let us put it here, and this is the center of the ship, and you have here G0, the initial center of gravity, and this tank is now filled up to this height with some liquid, and let us say that the center of gravity of this liquid is at small g0, and it has a small weight, it has a weight equal to small w, and the capital W represents the whole displacement of the ship, which is tank plus everything in the ship, the whole displacement of the ship. Small w represents the weight of the water alone. let us call it water for time being. It can be oil also, it does not make any, it only difference is in that row that we will see. Then the center of gravity of that small water body is G0, small G0 and capital G. Then this center of gravity, center of buoyancy is B0, and let us put the meta center here M. So, these are the now what happens, let us suppose that the ship heels, ship inclines. Now, this will also move on its own, means first of all the ship will incline, let us say like this. Now, this body will also, this surface of water will no longer be horizontal, it will start it will move in its own. Now, let us draw that figure. W1 L1, this is W0 L0. Now, initially, so here you have this tank, it has its G0, and now it is, because of that inclination, this is like this now. Okay, the water surface is like this, and because of this you see that more water is there on the right side. So, G of that water body will shift to the right. So, this will be G1, let us say. Okay. This is just the G of that water body, that is small g always represents the of that small water mass alone. So, that is small g. Now, let us say that, so this becomes, if you think of it, if it has really become similar to that problem we did of shifting of mass, that is this small weight W, that is the weight of that water, is actually shifted from G0 to G1. It is almost similar to that problem. Now, what has happened, let us say that G0 is its capital G0 is the initial center of gravity of the whole ship. Now, because of a weight shifting G0, this will shift to here G1, okay, and here this will be the vertical, okay, this will be the vertical, and let this be Gv. Then so, this figure is very much like that of a center of buoyancy shifting and the meta center. So, you have G1 and Gv, okay. There is similarly, okay, that figure explains it. Now, let us derive the expression. Okay, now, let us do one thing, let us assume that in this derivation this is a box, it makes the derivation simple. We will do it for general later, but first of all let this be a box, we have already said box shaped barges. So, this is one of those, and because of that, and let us call the distances as let us say that this distance is b, small b. Now, so this, what will be this distance, I mean this G0 is b by 2, it will be at the center, right. G0 is the center of gravity of that water body. So, B0 is the B is the breadth of that tank. Now, G0 is the position of that, we are talking about the horizontal position only, we are talking about right now, forget the vertical movement. So, that G0 is initially at the center, because it is a rectangular box and water is like this, means it will be at the center only. So, this is G0. So, it is initially let us say 0, or it will be in this case b by 2 exactly at the center. And what will be G1, the distance of G1 from the center? Now, what do we have? We have the small wedge that has moved to the right side. Now, what do we have to find? We have to find the center of gravity of this triangular wedge, therefore, it is 2 by 3 b by 2. Okay. So, this is it clear, or should I? Okay, it's anyway. It is the same problem that we did. Means like this. See, we took this whole wedge, we took this wedge, we found the center of gravity shifting. The only thing is, in this case, we are just taking the small region, this small region. So, it is this wedge has shifted to this side. So, one wedge has, one side has come down, one side has gone up. So, G has shifted. So, this distance is 2 by 3 b, no 1 by 2 by 3 b by 2, okay. That is that distance. Now, with this figure here, this figure we need, let me derive things here. Okay, that is, first of all, what is G0 G1? I will just write the value, then if you want I can explain it. Is that clear? Because this we have explained many times, that is this is the value of G0 G1, which is the moment of, that is what do we have here? We have a small mass small w inside a huge, the whole mass capital W. When that small mass is moved at distance d, we have seen that the moment of the center of gravity of the whole system is small w into d divided by whole weight. So, that is what this is. G0 G1 is the distance through which the center of gravity of the w has shifted. So, w into G0 G1 by capital W. So, that is now we can write this, okay, this is obvious, volume of that wedge into rho of that water, okay. Weight of that is, okay, actually they are talking about mass, not weight. So, W is equal to V into rho I, okay. Now, what is V? V is this volume of this wedge. What is the volume of the wedge? Volume of the wedge is area of the triangle into the length. Now, what is the area of the triangle is half base into altitude, base is b by 2 into altitude is b by 2 tan phi. Note one thing, what will happen is that the ship is like this, okay, and the surface of that, what there is tank here and there is a liquid inside that liquid, that surface is also horizontal, it will be horizontal, because if the ship is horizontal, this will also be horizontal, then it tilts like this, in this case yes, it tilts like this. Then what will happen is that this will also tilt in the same fashion, therefore, it will tilt by the same degree as the surface as you can just look at this figure, means this angle is phi, similarly this angle will also be phi, it is as it's both are similar, okay. Therefore, what I am saying is this, if this distance is b by 2, this distance is b by 2 tan phi, because this angle is phi, this is b by 2 tan phi, b by 2 tan phi divided by b by 2, that is tan phi, into the length L. Therefore, weight on and tan phi, because we are talking about small angles, we replace it with phi. So, therefore, the weight small w is equal to L into b square by 8 phi into rho I, okay. Rho I is the density of that fluid, let us call it water, it is therefore equal to 1000 kilogram per meter cube. That is your that is the weight of that fluid that is being transferred. Then you have G0 G1 is already given, it is equal to now what is G0 G1? G0 G1 is it is 2 by 3 2 by 3 into b by 2, yeah, b by 3. Now, that is, this is now what is actually here, we are trying to find out the movement of the mass, means here actually I made a small mistake here, that is this G0 is actually let us call this G0, let us call this G small g2, okay. Now, what is small g2? I will tell you, that is see initially you had, so what are we saying? We are saying that what initially this wedge, initially the system is at G0, okay, because the fluid is at G0, the center of gravity is at 0. Now, it because of this shift, it looks as if a small weight it's not looks as if, that is actually a small weight has been lost here and a small weight has been gained here, that is how it is. The weight lost is at a distance minus G1 to the left, the weight gained is at a distance G1 to the right, the center of gravity of that. Is that clear, or should I repeat that? That is, G0 is a center where you have the center of gravity of the initial water body, which is there is center. Now, because of that, something comes down here, something goes up here, water comes down here, water goes up here. So, a small wedge is lost here, small wedge is gained here. So, it is like this weight has been shifted there. So, from the center of gravity of this point, it is moved to the center of gravity there, that is the distance through which the weight has shifted, right. So, minus G1 to G1 is the, or G0 minus G1 to G0 G1 is the distance through which the body has, the weight has shifted. If this is not clear, you won't understand this. So, if you want, I can repeat it, it's not a problem. Do you understand it? Okay. So, it will be twice this, means this is the distance through which the this is not G0 G1, it should be 2 G0 G1. Okay. You have to clearly understand. So, this will be twice this into 2. So, this will be 2b by 3, twice G0 G1. So, what you are checking is one weight is lost at one point and one weight is added at one point. It is almost as if one weight has been transferred from one point to the another point. It is the same thing, here minus W, here plus W. So, this weight is transferred from here to there. So, because of this weight, the weight transferred is the weight, both the volumes are the same, otherwise you cannot do this problem, it becomes very complicated. One volume is different from the other volume, means you have to do different other things. We are not bothered about that right now, this is a simpler case. So, a weight moves from this point to this point, as a result it moves a distance of this 2 by 3 g 2 by 3 b, where b is this whole distance. So, through that distance the center of gravity has shifted, this much distance, horizontal distance, okay, horizontally that much distance has been shifted. We are talking only about horizontal movements, okay. Then you get that, then okay, then let us just finish this calculation. So, W into it becomes W into 2 G0 G1, 2 G0 G1 is 2 b by 3 into W, W is L b square by 8 into phi into rho I divided by, is there anything else, divided by W, right, divided by W, 1 minute, yes, what, oh, W is not, that W is replaced by this, yes, correct, that is equal to this and divided by W, capital W. So, this will be the distance through which G0 G1 will shift, capital G0 G1. Now, we can do one thing here, let us simplify this, 8 24. So, this is 12. So, this becomes LB cube by 12 into phi rho I divided by capital W. Capital W is the whole weight of the ship. Now, look at LB cube by 12. What is LB cube by 12? It is a moment of inertia about that axis. Okay. Therefore, let us call this I phi rho I by W. Now, of course, you might wonder, is it true for other shapes as well? Means, is it just for a rectangular box that it coincidentally becomes a I, or does it happen for all? Actually, it happens for all shapes, you will get I there. So, that we will see, but this is simpler, you can look at this and you can understand it very clearly. So, you get it as LB cube by 12 this, which becomes LB cube by 12 I replace by I, which is the moment of inertia of that water plane about that longitudinal axis. Okay, about the longitudinal axis. Now, therefore, G0 G1 is that this is G0 G1 is equal to this, that is once you have that. Now, we can do one more thing, G0 G1, let us look at this figure. Now, G0 G1, okay, this is a horizontal movement of G. So, this angle is 90 degree, this is vertical and this is therefore horizontal 90 degrees. Now, we can, this angle will be phi. If this angle is phi, these are all geometry, if this is phi, you will see that this becomes phi. Therefore, G0 G1 divided by G0 GV is equal to tan phi. Okay. Therefore, G0 GV is equal to, and which this let us write it as phi. Okay. Then G0 Gv is therefore equal to G0 G1 by phi. Therefore, this is G0 G1 divided by phi. So, you remove that phi, this becomes I rho I divided by W. Actually, there is no why this I is written, I am not sure, it's rho, the density of that fluid. So, you have this is G0 Gv. Now, I do not think that derivation is given, but G0 Gv will be the actually the distance through which the center of gravity of the ship moves in the vertical direction of the ship. Now, this liquid, right, what we are saying is, no, looks confused, but I will tell you what this is. That is, see, this liquid is moving like this. Okay. When that happens, the center of gravity shifts both in the vertical and in the horizontal direction. What we derived G0 G1 is the shift in the vertical direction, in the horizontal direction. Okay. Therefore, we are finding out this shift in the vertical that we will come to later, but just remember this expression G0 Gv is equal to I rho by W, we will derive it. Then, so actually this, why is it called Gv? It is called a Gv because it is called a virtual center of gravity. Virtual center of gravity, that is, when the free surface of the fluid, means when the ship is like this and the free surface is moving up and down like this, that is, the body is tilting like this, inclining like this, and because of this the water inside the tank is moving up and down like this. Because of that, the center of gravity of this is going up and down. Okay. Now, when that is happening, the center of gravity of the ship also goes up and down. So, that movement can actually be represented by this Gv. Okay. Then, okay, actually they have just written it here. If you do the whole set of derivations for what is not a rectangular body and just a arbitrary type of body, actually you will end up like this. Okay, 0 to L, right? Yeah.
Sir, how does this center of gravity move?
How does it move up? Because the center of gravity of that free surface is moving up and down.
The center of gravity.
No, this is like this, right? This free surface is like this. It moves like this. Free surface, so its center of gravity moves up. It's moved horizontally and it moves up also, because something has come down here, something has gone up there. So its center of gravity moves up. Because the center of gravity of the free surface of the liquid moves, the center of gravity of the ship moves, because it has to move, no? Yeah. Okay. Then, so in this case you get V into that derivation. If you want, we can do the whole, that is, instead of that LB cube by 12, it will become like this. Okay. It does not matter, just you can take this formula for granted, that is G0 Gv is equal to I capital I into rho divided by W. So, this gives you the distance through which the center of gravity moves in the vertical direction, and we have before expression that gives how the center of gravity moves in the horizontal direction, G0 G1 I rho phi by W. That is obvious, because G0 G1 by G0 Gv is just phi or tan phi. Tan phi is phi in this case. So, this is one thing. All right. Then, we can do some simplified cases. We will do it here. That is, two things you have to notice. It is interesting actually, because this movement of the center of gravity is actually, you are seeing, it depends upon I. Note one thing, this is not I of the ship. Let me see where I derived it here. Now, see, this is LB cube by 12, which is L is the length of the tank. It can be the length of the ship also. If it is the whole length of the ship, the tank extends the whole length of the ship, it could be the length. But remember, and this B is actually the breadth of the tank, not the breadth of the ship. So, this LB cube by 12 represents the moment of inertia of the tank. So, here if you have the whole ship like this, if you have the whole ship here, the tank is just here, this is the moment of inertia of this tank about this center axis, you have the tank here. About this center axis, what is the moment of inertia? This is the center line of the ship, and this is the whole ship. So you have a whole ship, you have a small tank here, you have the center line of the ship, this is the center line of the tank itself. So this is the moment of inertia of the small tank about its center line. So that is, now we can see one thing, how does the which are different ways, for instance, to change this G0. Now we have already seen Gm is affecting the stability. We know that, because Gm, we know that Gm has to be greater than 0, which implies that what is the best way? You should have G as low as possible. That means Gm will be large. M, so let us suppose that M is fixed. If G is as far down as possible, then Gm will be as large as possible, and you will have maximum stability. Therefore, our idea is to reduce Kg as such. Okay. We are trying to reduce Kg. Now in this figure, if so I said according to this figure we have to reduce Kgv, means the distance between G and Gv should be as minimum as possible. That is our goal, that should be one of our goals. Now what are different ways to do that? Now G0 Gv is now depending upon I. Therefore what are we trying to see? We are trying to find out different ways to reduce I, because we want to maintain the stability of the ship. What we are seeing actually is that if you have a ship, you have a tank in it, you have a free surface in that tank. If the ship heels, and if it is while it is moving, while the ship heels, of course there is a loss of stability because of the heeling itself, but because of the tank and that free surface effect, there is an additional loss of stability than if the tank is not there. So if the tank is there, there is an additional loss of stability, and that loss of stability, let us see how we can minimize. We cannot do away with the tank, we need the water or we need the oil, so we cannot do away with the tank. So what are different ways of reducing that reduction in stability? How to improve the stability? That what, so what we can do is, now what is I? I in some ways can be written as LB cube by 12. Now what we do is, suppose that is, we are looking from the top now. Okay, let us suppose that this is a ship, and let us say that tank is like this. Okay, let me draw a big tank. Therefore you have a ship, okay, on that ship you have a large tank. So what do you think is a partition it exactly? What is a best way to do that? That is what we do. What we can do is, we can partition these tanks exactly. That is what they do. So instead of having one large tank, you can partition the tank. What you see here is this, how much will the I change? I will become L into what has B now, it will be, let us say that it has divided into N, okay, N compartments, it becomes B by N. So it becomes B by N cube by 12. Now you have to sum up the i's to get the total I, so you have to multiply with an N, but still it is reduced many times. It is B by N cube into N, so it is, yeah, L B cube by 12, and there is an N square, it is reduced N times, N square times, it is reduced N square times. So this is known as longitudinal. You know that this direction is called longitudinal. So longitudinal subdivision, longitudinal subdivision of the tank, of the whole tank. If you divide it like this, you end up with a very low value of I, which implies that it does not affect your stability so much. Now what will be the case if I divide the tank like this, transverse? What will happen?
No change, sir.
There is no change, exactly. It is because I will become what? It will become L by N into B cube by 12 into N, right? It becomes same thing. So there is no point in transverse subdivision. This is called transverse subdivision.
But sir, when you consider the transverse swing of the ship, sir,
Transverse?
swing of the ship,
We are talking only of the transverse swing of the ship.
also we are talking the longitudinal swing.
What is longitudinal swing? No, no, no. We are not at all. We haven't talked about, or in fact, we won't be talking mostly about longitudinal movement at all. By longitudinal movement, no, it's just that it's not in that course. That's all. This is more. One of the reasons is that, for one thing, that is this movement is not affecting stability so much. That is, see, this length is very large. A small movement like this or like this won't affect the ship. It won't cause it to capsize and all. We are talking about capsizing like this. It's very rare chance. So this is more important. This, when it tilts in a transverse section, that is, As I told you, what is this called? We already mentioned that trim. We called it trim. Now this movement we call it as heel or list. Okay, so heel is more important because since this distance is very less, very strong wind, for instance, when it hits like this, it won't capsize it, but it can cause it to move very large distance. So this we are only discussing transverse stability. Of course, there is a separate section on longitudinal stability as well, but it's there at the very end. If we have time, we will do it. So this is more important. So only we are only talking about transverse movements, or these movements are called heel, and such dynamic movements are called roll, which I have already mentioned. Dynamic movement means it keeps moving like this. This vibration mode is called roll, and just that static movement is called heel. Means it's like this, it moves like this and stays there, it's called heel. But if it just moves like this, it's called rolling. That process is called rolling. That's what we are talking about. We are talking about healing right now, hydrostatics. Rolling actually comes in hydrodynamics. You know the difference between hydrostatics and hydrodynamics. Dynamics is about motion, it's about fluid motion and the result of that on the ship, and hydrostatics is about the effect of like pressure, forces. It's a static case. What happens, just movement, that's all. It's not about continuous movement. Okay, so this is a very important point actually, because again in your vivas they will ask you this. Means first question is what is free surface effect, but more important than that, these are kind of trick questions. Means this shows how you have understood the subject. That is this question: why is it that you do longitudinal partitioning and not transverse partitioning? What is the reason for it? That's a very common question in your job interviews, and your it's like another question similar to this is, they say for a submarine what will be your BM? That's a common question again. I told you about that. That is BM, we have seen that I becomes 0 in that case, so that when it is under the water, and therefore that is again 0. That is one of such problem, one of the such questions. This is another one. Why is the longitudinal partitioning? So this is the reason. Okay, you should remember this expression for I, and this is how it becomes by n square. In this case, by n into n cancels out, there is no effect. Okay. Now we have some 2 or 3 questions here, problems here, that gives some understanding actually these kind of problems. That is, it says that a vessel has a displacement of 10,000 tons. So or you are given kg is equal to 8.9 meters. I mean these are okay, and km is also given. Now you are told that the vessel is now going to load ballast water of some relative density into a rectangular tank, and the length of the tank is given, and the breadth is given, and the depth is given. Okay. So these 3 things are given. Now they are sent, this tank is now divided into 2, or rather it is a double tank. So it has a center line division into 2, it's divided into 2 tanks in the middle, and you are told that the kg of ballast is equal to something, and you are asked to find the GM. Now it's sometimes mentioned like this, they say find the fluid GM of the vessel. The meaning of that is, or fluid kg, it's any of these. The meaning is that in the presence of such a free surface effect, in the presence provided that the tank has the fluid, what is the GM, what is the kg? Okay, this is the meaning of this fluid. So the question is to find the fluid GM of the vessel. Okay. Now first of all we can find the weight of the ballast. Is given by the length of the tank into breadth of the tank into depth of the tank into the density of water. You do this, you will get the weight of the ballast. Then you are given the kg of the ballast. Now, what we can do is, so when you do this problem, you will see in the book it is written like this. That means kg without the fluid, just with the ship, that is this, and this is kg with the fluid. So, water is added, that is ballast is added to the tank, and then what you have is a kg of the fluid. Okay. So, now what we can do is make a small table. That is, note that we need to find the kg of the ship with the fluid. So, we have already done many times how to find the kg of a complete system when you have 2 or 3 weights. So, first you have the weight of the ship itself, let us call this weight of the ship, and it has some kg. You do not need to do the problem here, I will just explain it, and you find the moment of that weight, that is this just W into kg. So, that gives you this moment. Then you are given the weight of ballast. So, you put here the weight of ballast, and you are given the kg of the ballast. Okay. The problem says you are given the kg of the ballast. Then you find the moment due to the ballast, find the total moment, find the total weight, and that will give you kg as the moment divided by weight. Okay. This is the actually this is the initial moment before the fluid has healed. Is it this is given here? Wait. Okay, it is not specifically told, but you have to assume that, otherwise there is nothing in this problem. So, you have to assume that the ship has healed. Now, this is the kg. Now, in this case the fluid is just added, because of it the kg has shifted, and now the body is tilted, inclined, and because it is inclined, its kg will move, or I mean its g will move. The free surface effect is happening. Of course, free surface effect was there before also, but it is inclined now, and this, because of this free surface effect, what will be g 0 g v is the distance through which the center of gravity of the ship seems to have shifted. This n square represents the tank. We have already seen how it comes. It is a longitudinally divided. We have already told in this example, you have a whole tank, it is divided into half in the middle. So, you have n equals 2 here. So, this is I into rho by W into 4, okay, because n is 2 here, it is divided into 2 sections. Now, of course, these are the regions where you have to be careful. You do not find the I of the whole ship, you do not find I of the water plane area of the ship. That is not what this I represents. This represents the moment of inertia of the tank surface. Okay. This is the moment of inertia of the tank surface. I will keep it here. So, that is just equal to, okay, we will just do that. I is equal to, it will be L B cube by 12. So, this will give you the I of that surface. Note that B is the breadth of the tank, it is the total breadth of the tank, because here means you have a tank like this, you have a tank like this, it is divided like this, and if this is B, okay, then this should be B. Okay, you have to be careful. All these things, just go to just remember the derivation. B by n comes because the whole B has been divided into n, that is why B by n came. Therefore, B is the total tank width, not the width of each compartment. B is the total tank width. So, or you have to do one thing, you have to find I of each tank and you sum it up, means you multiply it with, in this case there are 2 tanks, you find the I of one tank, you multiply it with 2, you will get I of the whole thing. Either way you do, but just remember that this is I of the tank. So, this is L B cube by 12 into 1 by n square. This will give you the I of that system. then therefore, then G0 GV will become this into this value I into rho by W. So, this will give you the distance through which the center of gravity seems to have shifted, the vertical distance through which it has shifted. Now, here I'll a little change I'll make to what I said before, that is, I said that kg solid represents the weight of the ship without the fluid. I'll make slight change to it. It's not without the fluid completely. What it is actually kg with the fluid, but without inclining. Means there are two. The other thing is also called kg solid. So I'll write it here so that there is no confusion. So first you have the ship alone. That is also kg. It is 1 kg. I mean, these values will be different. This is also a kg solid only, but let's call it 1. Then there will be ship plus the fluid. That is also written here as kg solid. Let's call it 2. Its value will change. Why? Because the new weight has been added, so kg will shift down. It will shift towards the water. Okay, it will shift towards the keel. Then this is ship plus fluid heeling. Means it's no longer in an upright condition, it has heeled. In that condition, what you get is what you call as kg fluid. Okay. Now, here you have your initial kg and now you have your kg solid 1 that we have already calculated using that table, like using this table we have calculated this kg. This is kg solid 1. Okay. So, that is calculated. Now, you need to find kg, no, this is kg solid 2, sorry, I am confusing you. Is kg solid 1 is actually just this. This is, it is just the ship alone. Okay. The kg of the ship alone without the liquid being added to it is what we are calling as kg solid 1, that is this. Now, to it fluid has been added or water has been added at the bottom and still it remains upright. It is not heeling or anything, it is remaining upright, but water has been added. Then what happens? Therefore, you have kg solid 2 and then it heals, okay, and it becomes a kg fluid. Okay. So, kg solid 2 we have already calculated. How will you get kg fluid? Instead of this new G0, I mean the old G0, we replace it with GV. So, you get your, so instead of G0m which we have, which was initial, it is actually GVM. Okay. This will, from this what kg you get is the kg fluid, it is not equal to kgm. So, you use your GVM, you have to get that is, you have G0 GV. So, it is very simple actually, to that kg solid if you add this G0 GV, that will give you the distance through which kg has shifted up, that will give you your kg fluid. Means it is very obvious, that is, so if this is the ship, if this is your G0, this is your GV. So, this is K, to K G0, if I add G0 GV, you will get K GV, which will give you the new position of the center of gravity of the ship by the presence of the heeling of the fluid. So, this will give you kg fluid, and from kg fluid if you want, if the question is there, you can find GVM. Okay. The only thing you have to know is that this is the final position of your center of gravity because of the heeling of the fluid. Once you know that, then you just think, I mean, what is your new GM, what is your new kg. So, your new kg is kgv, your new GM is GVM. So, once you know that, you can do this. Okay. Then okay, now these are the kind of problems that you really come across in when you are doing a real design. That is, you are given that there is just a double bottom tank. Okay, there is a tank Now, they have given you the half ordinates of this tank. Okay, this is the second problem. So, you are given that right now we are not having a okay. Now, you are given the half ordinates of the tank. So, okay, the difference in this problem is that this is not a rectangular tank. Okay, so it becomes a little difficult to find the eye of the tank probably, and yeah, it's just the problem in finding the eye of the tank. So, the it's actually so what they are given is this, that is for this tank you are given the let us divide this in same way as stations and half ordinates. That means that you have this whole tank, long tank, from the, let us say this is the aft of the ship and this is the forward of the ship. This is divided into stations. Okay. Now, you are going to divide this into stations. Let us start this from, maybe let us start from here itself, station 0 to 1 2 3, and it is not a rectangular. Okay, it's some shape, it's a tank of some arbitrary shape, and you are given the half ordinates. The meaning of half ordinates is this. Okay, these distances are given. So, from the center line you are told what are these distances. Remember, it is not a rectangle as this figure shows, but it's a different y's are given, y1 y2 like this. So, these are the half ordinates. So, station 0 1 2 like that, you are given the different half ordinates. So, your problem is to find the same thing, to find kg fluid. So, the only additional thing you have to do is you have to find the eye of this tank. That is the only additional problem. Actually, I probably need not do this, because we have already done a problem before to find the eye of a water plane area. Okay, that was for a ship, but this you must be knowing how to find the eye of this tank, because I have done half ordinate cubed. If you remember, I have done a half ordinate cube, then I did a summation of the area of half ordinate cube. If you want, I will write the table, but actually we have done this. So, this is the way in which we can make the table. This is a function of area. This becomes a half ordinate cubed. Simpson's multiplier is not needed again, but it's a function of the moment, second moment. So, you have like this stations. Now, half ordinates are given for each station. Okay, you are given these values. Simpson's multiplier we know. Okay, 1424 we are using. This is the first rule, Simpson's first rule. Then now, what is function of area? Function of area will be just this into this. I will write it if you want. 1 2 3 4, this is 5 6 and 7. Now, the fourth column of the table will be fourth column of the table will be second column of the table into third column of the table. I mean, we have explained this too many times, I think I will leave it. So, 4 is equal to 2 into 3. Then similarly, we have also derived the moment of inertia. So, I will say that 7 is going to be half ordinate cube, that is 5 into 6. This is again 1 4 2 4. This will be this thing cubed. It is actually 2 cubed. Okay. So, your column 5 will be column 2 cubed, which is half ordinate cubed, and when you do 7 is equal to 5 into 6, and then this will give you some i's, function of i's. then you will have to sum up that I. Okay, you will have to sum up that whole thing, and finally here you will get the I to be h by 3 into summation of function of I. Okay, is that I think h by 3 is the distance between the stations, and so what you are doing is you are actually summing up the i's, LB cube by 12 in fact, or integral of B cube dl. Okay, that you are doing for each, you are actually finding each L B cube into dl and you are summing it up. That dl is fixed as h here, so that is that h by 3, and that is of course the summation. So h by 3 into summation of function of this I, this will give you the I of the section, I of that tank. So other than that it's exactly similar as a previous problem, so it's okay, I won't repeat that. So this is the thing you have to do. We can kind of combine the previous section with this section and make it look very complicated, the problem look complicated, but there are a couple of things if you know, like these formulas whatever I have derived about the free surface effect has to be very clear. You have that formula should be clear and you should know what each term stands for, and once you know that, then of course, and another thing is you have to know all this, you have to know how to find i's. This way of finding i's using means not just the LB cube by 12, but finding I in case you are given an irregular shape. Okay, you have to be able to find the I, you have to be able to find the area in case of volume or the displacement. So these three things, that's all, area, volume and moment of inertia. So these three i's you should be able to calculate it, provided you are given the station and the half ordinate. So once you are given the station and the half ordinate, you should be able to calculate the I like this using this table. Once you have the I, note that this I goes into that equation, that's all. This final value, it's just one value of I for that whole tank about that central axis. Once you have that, you just substitute it into the previous equation, that is I by rho, I into rho by W, and the second, that is the second part, that is of course very straightforward, and you get kg for the fluid. Okay, and so what you are going to see is that when there is such a case of adding a fluid, means adding a fluid will reduce, actually what is going to do is okay, this is the net result, that is when you add a fluid to a body in the ship in the form of a tank in such a way that you do not completely fill the tank and leave part of it free, then you end up with a free surface effect, and this effectively ends up reducing your GM because your G moves up. So it was initially like this, you had your M here, you had your G here, because of this free surface effect G moved to this point GV. Okay, as a result your GM is reduced, it's now it's equal to just GVM, which is less than your GM. So your initial GM, so you have a lesser GM, and there is condition for stability to be lost. Okay, so and one way to change that is partitioning the tanks, which will reduce your I, which will reduce your reduction in G. Okay, means it will prevent your G from going too far up. So just know these things, that is in a ship you should basically have your center of gravity as low as possible. Of course there is a other side to it, actually that might come in the next class. I mean you cannot have the G too far down, there is another problem that will come up, but in general from our study so far you have to conclude that G should be as low as possible. When G is as low as possible, GM will be as high as possible and your stability will be very high, and you will be in a good condition. Okay, the ship will be safe. Okay, thank you.